Okay, so what we're going to do in this video is we're going to look at what's called buffer capacity. So one of the things that we learned when we did these experiments was that we could use these buffering solutions, right, where we have the acid and the conjugate base, and that we could look at the pH values of these as these chemical quantities changed. And what we found is that the pH value stayed relatively the same, right? And we used the Henderson-Hasselbalch equation to calculate these. We found that the deviations of the pH were small. Okay, so what we're going to do now is kind of quantify that. Well, what does that mean? Why do buffers work the way they do? Now, buffering capacity, it means, so when you add, the thing that's unique about buffers is that when you have this weak and its conjugate in the same solution together, it could be a weak acid, conjugate base, or a weak base and its conjugate acid. When you have these pairs in solution, when you add either protons or hydroxide, the pH doesn't change much. Now, that happens over a certain range. It's not sort of what you would call infinite. So every buffer has a capacity to where it's able to keep the pH constant. But once you go past a certain point, of course, it will behave like an acid or a base in water. So the buffering capacity is the amount of acid or base that can neutralize. It's going to neutralize it before the pH of the buffer changes to appreciable degree. Now, buffers resist change in either direction when concentrations of the weak acid and the conjugate base are about equal. Right? We learned that is when they're about equal, then what happens is that this is pretty close to 0 and the pH is constant. The pH is constant. Now, I can make some changes in here and I may add small amounts to this. That's what we're going to show next. But it's not going to be an appreciable amount because the pH is still going to hover really close to that pKa because this is going to be really, really small, if not 0. Okay? So, a pH range of a buffer is usually about plus or minus 1. So if something has a pKa of 5, it can buffer with pHs 4 to 6. Right? So it can buffer a little bit below and a little bit higher. Okay, now a couple more things about buffers and then we'll go on and kind of get here, which is really testing out this idea, well, how do buffers work and why is it that they are able, when you add acid or base to it, keep the pH right at that pKa. All right. The pH of buffer A, so I've got two buffers here. One's at 1 molar of the weak acid, 1 molar of the conjugate base. This is 0.1 and 0.1. Now, buffer A and buffer E, the pHs are equal to each other. Now, the reason that they're equal to each other is because the concentrations of these is 1 and 1 and 0.1 and 0.1. Even though they're different, this is still 1, this is all 0, and my pH is going to be equal to my pKa. So they're equal to each other. But buffer A has a greater capacity because there are more moles to react. So when I add an acid or base to this, and I have that buffering capacity, I've just got more moles here than I do here. So it's going to have a greater capacity. Now, when I make a buffering solution, I need a couple of things. I need to know, if I know what the pH is that I'm interested in staying at or I'm interested in, I need to pick an acid with its conjugate base that has a pKa around 9. So this has a pKa of 9.31. This one has a pKa of 3.77, and so this is the one. So this is a pH range I'm interested in. This is the acid I need. The only other thing I need now is my conjugate base. And so that's going to be this. And that could be sodium cyanide, potassium cyanide. You could deliver that as a salt of some sort. Okay. All right. So let's see how this works. So I've got this buffer. It's 1 molar acetic acid and sodium acetate, and this is the one that we looked at in the previous video. Had a pH of 4.74. Okay, the volume is 1 liter. That's going to simplify things a lot. Now I'm going to add 10 milliliters of sodium hydroxide to it. So the first thing I want to do, again, as we always do, is we're going to find out how many moles this represents. Now, my equation that I have here, I'm not going to write it like this. I'm going to use the same C2H3O2H plus hydroxide gives C2H3O2 minus plus water. Okay, so that's what I'm looking at here. And we looked at this in our particle diagrams as well. So I'm going to add this to this weak acid, and I'm going to pull off protons, and it's going to go to the acetate ion in water. So I'm going to add about 1 milliliter of that. Well, if I want to know what's happening here, I know when I add the hydroxide, this concentration is going to go down a little bit, and this concentration is going to go up a little bit. Has to be, because I'm pushing the reaction in this direction. But by how much? And let's look. Now, first of all, I want to know how many moles this is. 1 milliliter of a 10 molar sodium hydroxide solution is 0.01 mole hydroxide. So that means that since it's a 1 liter solution, that means it's 0.01, because even though I added, you might ask, but you added that 1 milliliter. We're going to kind of ignore that volume because I've got a whole liter. You could put 0.99 liter or 1.01 liters if you wanted to, but we're just going to assume that it's still at about 1. And so the molarity of this is, we're going to keep that the same, the molarity here. So what I have then is I have 1.0 mole, right? Because that's what I started with up here. And I'm going to subtract 0.01 mole because I'm reacting it here. I'm going to subtract it, and it's going to go this direction, and that's going to give me 0.99. I'm going to leave my concentration as 1. My volume as 1, so I'm going to call this molarity. And then I'm adding 1 mole to this because it's all that whole 0.01 moles of hydroxide is adding to what I had to begin with, which is 1 plus 0.01 mole more. So there's my ratio. So if I put all this in the Henderson-Hasselbalch equation, C2H3O2, I'm used to writing acetate a different way, but I want to try to stay consistent here with how they do this in the textbook. Right? So that's equal to the pKa is 4.74 plus the log of 1.01, because that is this one, that is my base. Remember, it's base over acid, 0.99. So that is equal to 4.75. That is going to be the pH after I've added 10 milliliters of sodium hydroxide to this buffer. Why is this remarkable? Well, let's just calculate what would happen if I added 1 mil of a 10 molar solution of sodium hydroxide just to pure water. So 1 milliliter, this is 1,000 milliliters, is 10 moles, is equal to 0.01. It's in 1 liter, so that's 1 liter. So that is a concentration of 0.01 molar hydroxide. So if I want to know the pH, I'm just going to do the negative log 0.01, which is equal to 2, and 14 minus 2 is equal to 12. So here's what we have. If I were just to have added that 10 milliliters of sodium hydroxide to water, it would give me 12. The buffer lowers that pH and keeps it right close to that pKa. Okay. Let's try another one. Let's add acid. Let's go the opposite direction. This time we're going to add 0.01 mole of H+. So my reaction this time is now I'm going to react with acetate. It's going to react with the acid and make acetic acid. Okay, so that's what's going to happen there. So the amount of buffer that I'm going to have this time, this is going to go down and that is going to go up. This one is going to be 1.01 molar. This one is going to be 0.99 molar. Plug all that in. 4.74 plus the log of now, it's going to be 0.99 divided by 1.01, which is 4.73. So again, if I were to put 1 milliliter of HCl in there, so 1 milliliter HCl, 1,000 milliliters is 10 moles. That would be 0.01 molar. Negative log 0.01 is equal to 2. So again, if I were just to have put that HCl into water by itself, I would have had a pH of 2, but I've kept it at 4.73. So it's just basically hovered around this 4.74. So this is my pKa. So I've basically gone either up to 4.75 or down to 4.73, and has kept it right around that pKa because this ratio changes, but it doesn't change enough to make an impact on that. So that is what is meant by buffering capacity.